All right, folks. So we're so here we are today, April 12th. So we're going to be doing 1.3. Well, I'm not doing anything different. Is anybody else having the problem? Because if I have to reboot, it takes time.
I'm not having any issues.
Yeah, I mean, whenever you hear something going on like that, I mean, have an issue, restart it yourself because I don't see anything else I'm doing any different than usual. Because if I have to reboot, I mean, that's about the only thing I can do, restart it. Okay, so we're looking at 10.1, 10.3. Those are fairly short for the most part, but I'll try to go through them slow so we can kind of, I guess you would say, take advantage of every opportunity to learn these objectives that we got to deal with in here. All right, so here's our new worksheet. And just kind of keep in mind, I mean, we got this whole week, next week, and then we got one day, then the test, and then another day. So because this is class beats on Monday and Wednesday, we got one class on Monday that other people don't have. Hello, Trinice. All right, so they don't give us an example for this, but let me see if I can kind of give you something on the board to kind of set you up for this because it's not really an example thing, and I'll just kind of show you what I'm talking about. We'll come back to this here. All right. What we kind of need to know is a couple of things. I'm going to put over here. So, all right. Of course, one is not really an issue because one squared is one. Doesn't really change anything. But if we go down the line, 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared. And you could keep on going on and on, but for the most part, you're not. These get big pretty quick, especially the cubes. I'll go up to 9. And of course, most people know about 10 squared because that's 100. All right, now on the cubic side, 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. And I'm just going to go up to 5 here because these get big real quick. All right, so those are pretty standard, those squares and cubes. So what we need to keep in mind that if we run across these numbers when we're dealing with what's called a let me show you. All right, so it's a kind of a little hook thing there. It's not a division sign, but you know, it sort of looks like that because it's got a point there and that little crook. And the square root is the only one that doesn't have a number in there. And that's just because that's the base case. It's sort of like why we don't say x to the first power, because if there's no power up there, it's understood that it's just 1 power of x. Well, this is understood to be a square root, and the cube root looks just like that. So if we see something like this where we have the square root of 4, then we kind of just have to be ready to know that that's 2. The square root of 16 is 4. And the same with all of these. Square root of 81 is equal to 9, based upon these basic mathematical facts about roots, or perfect squares, I suppose I should say. Same thing here. Cube root of 8 is equal to 2. And then the cube root of 124, or 25 is of course 5. All right. Let's go back over here and let's look, because there's nothing really we can show as an example. So what would the square root of 49 be?
7.
Yeah, good.
7. I'm sorry about that.
So this is going to be 7. And that's because, I'll just kind of abbreviate because here. 7 squared is equal to 49. Another way of kind of looking at this, which is going to be helpful for the variables, but we generally don't write 49 as 7 squared. But if you put it in there like that, and you remember that this is also a 2 in that crook, what this does is that 2 undoes that 2. And so what pops out is a 7. All right. So that's going to be helpful for how we deal with the variables. Okay. Variables are different now. Again, think of there being a little 2 in there. And what I would just ask you, the way to do these, which is a lot easier, I think, than the numbers, is to take that 2 and divide it into the 14, and what do you get? 2 into 14 goes 7 times. So x to the 7. And this is because, and we're going back to chapter 5, remember our rule for product rules? When you multiply like bases, you add up. That's supposed to be a 7 there too. All right. So with the variables, like I said, it works out real neat. Even when we're going to see these down here that aren't perfect, but you take the number in that crook, which is understood to be a 2 if there's nothing there, and you divide it into there, and that handles that. So that being said, I'll tell you what, I'm going to just kind of go over here and show you. You can break this into 2. Whenever you got 2 things that are being multiplied, which is what that 25 is doing to the x to the 16th, you can break it up like this, especially if it makes it easier to understand for you. I'll do that for a while here until we get the idea, but this can be looked at as 2 separate ones that are being multiplied, and then maybe that's not so complicated to look at it if you put them into 2 different ones. So the square root of 25 is what?
5.
And then use your same trick that over here you did. 2 goes into 16.
8.
X to the 8. And then you can take these 2 and square them. So 5 squared is 25. And it's a square. And 8 times 2 is 16. Going back to our rules here about from the exponents. Okay. All right. So what about number 4? What do you think is going to happen there?
You're doing the same thing as 4, correct?
For number 4 here, yeah. The only thing I would just ask you to watch out for is that negative sign is on the outside, so anything that comes out gets that negative sign tacked onto it.
So would it be negative 9x 2?
Yeah, 2 into 8.
4.
4.
And then 2 into 20.
Y to the 10th.
Yes. And so if we square this part, in other words, 9 times 9 is 81. X4 times x4 is x to the 8th. Y to the 6th, y to the 10th times y to the 10th gives us y to the 20th. But this is negative because that negative sign is sitting out in front. So it's going to negate whatever comes out. Something very similar is going to happen with number 5. Give that a try and see if you can do that. The only problem with number 5, there's not just a negative sign in front of it. There's a number that's negative. So it gets multiplied. In a sense, what happens here with that negative is the negative 1 or negative sign multiplies everything. Doesn't change anything other than the sign.
So what are we doing? We're multiplying by the square of 4?
By the square root of 4.
So that would be 5, negative 5 times 2.
Yeah, let's kind of put the negative 5 like this. And the square root of 4 is 2. right?
Yeah.
And then the x square root is x cubed, right? Because
Right. Yeah.
Yeah.
the 2 goes into 6 3 times.
Yeah.
Now you're multiplying that, so take that in the next step. Negative 5 times 2 gives you negative
-10.
x cubed. We're still using all the other old math rules. When you multiply the numbers, and then the x's just come along if there's nothing to multiply the variables by.
Okay.
All right. Now, like I said, this all applies even for other roots. So just keep in mind which one of those is going to be a factor for the 8. See, that's no longer a square root, that's a cube root. So the cube root of 8,
What is that? 2?
yeah, that's going to be a 2. But I wanted to break this one apart here. So these are going to be multiplying. And anytime you got two things multiplied inside of a root, you can break them apart into separate roots. All right, so you can still do the same thing we did here with the square roots. 3 into 15.
5.
All right, and that's x to the 5th. Okay? And if you were to multiply this times itself, you would get 4x to the 10th. Multiply again, you get 8x to the 15. Now it's cubed. So we're dealing with cube roots. You got to think about 3 times multiplying. Any questions about that? All right. Now, if you've got a square root, there's no way you can take, well, with what we know now, if we take the square root of a negative number, there's no real numbers that multiply out to be a negative number. In other words, if you have from what we know about numbers now, that square root of -4 is what we call not a real number. And before this chapter is over with, we're going to learn about something that's higher than real numbers. But for right now, see, there's no number that we can multiply by itself and get a -4. Because remember, this is a square root. All right, because if you tried -2 times -2, you would still get a 4. And if you tried 2 times 2, you get a 4. And that's just kind of the way the rules work for squares. Anytime you square a number, you're automatically going to have a positive outcome. But if you've got an odd root like number 3, then it's entirely possible to take the third root of a negative number. Because 3 negative signs, multiplying 3 negative signs, gives you a negative number. So that being said, which one of these is going to be what we need here?
-4.
Right, okay, 4, and then we need a negative sign. So for this part, it's -4. Now let's just kind of look at this part separately for the x's and the y's. Because like I said, this is really the easy part if you can figure out the number stuff. Now 3 goes into 18.
6 times.
Yeah, x to the 6 times. 3 goes into 27. So there we got it. And you can test that and see that you will get the negative 64. And I'm going to show you what I'm talking about. Negative 4 times negative 4 times negative 4. Well, negative 4 times negative 4 is 16. And then the third negative sign gives us negative 64. All right. So that's right what we got right there. Good. That's where we want to be at. All right. I tell you what. Let's see. There's some value. Someone's over here. I wanted to kind of go through. I think this is All right. Let me erase this stuff here. So don't look at these until I'm finished erasing. I should have done this before class, but I got distracted with some other stuff. All right, so number 2, again, that's a square root. I just wrote, you don't ever see that 2 in there in a math book or online math problems because, like I said, it's just the same way you want when you see x, plane power x, you won't see a first up there for the power, but that's what it is. So I just put the 2 there just to show how it works. So let's go back up here. All right. So the square root of x to the 12th, what would that end up being? 2 into 12 goes 2 into 12. Is that correct?
Yeah.
Because x to the 6th,
Square.
x to the 6th is equal to x to the 6th plus 6, which is equal to x to the 12th. All right, what about number 2? We didn't go that far over here, but there are squares past 10, so
There'll be 11, right?
that's
11.
right. That's 11, and that's because 11 times 11 is 121. So the cube root of 64
4.
is just plain old 4 this time. Now again, a cube root, it's possible to have a real number root for a negative number. So
That'll be negative 10.
and that's right, because negative 10 times negative 10 so this right here would be 100, and then an extra negative 10 multiplier gives us the negative sign back. All right. So any questions about those?
No.
Okay, let me get my water. I forget to get my water. me see. We're not going to do these just yet, but get them ready. All right, there's one more problem on that sheet over there. The worksheet. All right, so let's go back over here. Now, for two of the rules for radicals is if we multiply something inside, we can break it apart, and that's what I showed you here. We can break this into two and deal with them separately if it makes it easier for us. But we also have a similar rule for division. And the division rule is, well, you can break it into two by doing this. Have a numerator. And then deal with those separately. So, what would we get if we try to simplify each of those? Do the numerator first and then go to the denominator. It's usually the easy way to do it. Square root of 36.
E6x.
And then x to the fourth, or half of that, is x squared. Down here, square root of 25 is 5, right?
Yeah.
And then half of 10 is 5. Now, if you can simplify here, you do it, but there's nothing. Oops, this is a y. I'll fix that. So, just based on what we call perfect squares or perfect cubes. Basically, you no longer have a radical sign anymore. These things all simplify out to be what we call rational numbers. Rational numbers is what we essentially the topic of the last chapter, meaning that it can be expressed as a fraction. And a rational number, all of these can be expressed as a fraction, like 7 over 1, x to the 7th over 1, and so forth. Even this one gets expressed as a fraction. But an irrational number is one that cannot be expressed as a fraction. And so, let me just show you what I mean now. Well, this is going to square root of it. So, let's just say, before you take the square root of it, it's 2. Well, let me show you something. If you take 2 and take the square root of it, it's 1.4142, blah, 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 blah. Notice how it fills up the screen. It fills up the screen because that's a decimal that is non-repeating, and it's just going to go on as long as we want to calculate another decimal place. This right here cannot be expressed as a fraction. So that's why this chapter is called irrational numbers. All right? It's not used in the same sense of rational, irrational, like with human convenience and somebody's rational means that they make calculated decisions, or they're coherent, and an irrational person is somebody that's supposed to be the opposite of that. It's different here. Irrational just means that it cannot be expressed as a fraction. And that's what's going to be the case with these right here. All right, we've got this one here. It says 72 x to the 15th. Now, what we have to do in order to simplify these is factor out any perfect squares. If there's no perfect squares, then it's basically already simplified. But if we have a perfect square in there, we're not simplified. And 72 can be written as 36 times 2. And if you remember, 36 is a perfect square because that's 6 times 6. The 2 is going to just be stuck in there forever. The 36 will come out as a 6. See, they break it apart using that property, product property of radicals that I told you about. All right. Now, on the x side, this is one way to do it, and I'm going to show you another way that I think is a little bit easier. But, okay, this is a square root. 2 goes into 15. Well, that's not an even number, so there's going to be something left over. But what's going to be left over? Well, if it's not even, then you take one of them off. All right? You take one of them
Professor
off.
Cruz, I can't hear you.
What's that? What happened? What did you do? Is anybody else not able to hear me? Hello?
I can hear you, but there's like
I
a
can hear you too.
loud
Yeah,
fan.
I mean,
Can anyone hear me?
yes, we can hear you. So, x to the 15. Since 15 is not an even number that's divisible by that 2, well, there's going to be something left over. And what's left over is 1x that stays in there. So you can either do what they're doing in there, is take that x, put it off over there, or the way I like to do it is 2 into 15 goes 7 times x to the 7th with the 1 left over. That's the best way usually to fix those things, because unless it's happening to everybody. So the 6 and the x to the 7th come out, so they're in front, multiplying one another. And then the 2 and the x are still under the radical, so they stay there, multiplying the 6x to the 7th. So these are good. She was going to come back, but I don't know what happened to her. Please wait a little bit. All right. So that's the final simplified version of this thing. All perfect squares are taken out. Now, these first couple are just numbers, so it won't be nearly as complicated to this. It'd be just like working with a 72. And then this one here is just going to be working with variables. So what does 75 simplify out to? Well, first of all, let me ask it a different way. Let's look at those perfect squares that we have. All right, which one of these perfect squares divides evenly into, what was it? Was it 72 or 75? 75. Which one of these divides evenly into 75?
None of them.
25.
25, all right. So, that's 25 times 3, correct?
Yeah.
The 3 cannot be simplified any further, so we know that we've got the simplification we need so far. We've still got to take care of the 25, but the 25 times 3 gives us 75. So then the square root of 25, again, you can break them apart if you want to. So there we go. And I'll just kind of show you here. All right. Let me see if I can find another calculator that's got it. I'll just do it on this thing. All right. So square root of 75 is 8.66025. So kind of keep that in your head for a second. Now, I'm going to take the square root of 3 and multiply. Wait a second, it didn't do it. I guess you got to hit the 3 first. Times 5 is equal to 8.66. See, that's the same thing as 75 square root, 8.66. So you know those two things are equivalent. It's just this is what's considered the simplified form. And it'll be easier to simplify other things if we're able to do that later on throughout chapter 10 and chapter 11. So try number 10. That one's similar. What does this break down into? And like I said, it
4.
may help. It may help. 4?
Yeah.
4 times what?
4 times 4 times 4, because 4 times 4 is 16 times 4, 32. No?
Okay. Well, we're dealing with a square root, so we're only concerned about the 16.
Oh, no. It's true. My bad. No, it's not 4 then, I think.
Well, it's going to be a 4. So that's 16 times 2 underneath the root. The square root of 16 times the square root of 2. And what does the square root of 16 come out to?
2 times 4, 4 times 2.
So you end up,
Professor Cruz, I'm sorry. What are we doing here? Like when you go to, all right, the 16 square root of 16 and square root of 2, we have to then turn around and do the square root of 16?
Right, because we need to pull out the perfect square.
Oh, so we're finding a perfect square. Okay.
The largest perfect square inside of 32, because now we're dealing with values that are not perfect squares. So now we're simply looking for numbers that are factors of 32. That's the largest perfect square in there. And that's 16, because that's 16 times 2 is 32. The 16 is a perfect square, so I broke them apart. And the square root of 16 is 4. And then the square root of 2 just comes along for the ride. So let me just show you that we got the same thing here. In other words, if I do square root of 2 times 4 See that? Those are both the same thing. They're equivalent. This is just what we call the simplified form because there are no perfect squares underneath that radical sign. All right? Let's see. I must have too many windows open because it's slowing down here. So this is what you're kind of trying to look at and determine which is the largest one of these is a factor for square roots. For if it was a cubes, then you would be looking at these numbers. All right, and then Trinise, sometimes it might help just to kind of click off your audio down there at the bottom and turn it back on, like the thing that says mute. Put it back on and turn it back on. That might be all you needed to do. All right, so what about number 11? That's just variables, and as I said is, if you imagine there's a 2 in there, how many times does 2 go into 13?
6 times 12.
Yeah.
At least 1 out.
So it's going to be x to the 12th.
Times x.
And then, yeah, and the x stays in there. That one's going to stay in no matter what we do because that's the irrational part. The square root of x to the 12th is x to the 6th times x. All right? So any questions about that one?
Mm-mm.
All right, let me go back over and look at those ones that I was erasing. I want to see. I want to see what we were, if we can look at any of those now. All right, some of these are, I'd gotten these out of my math lab to just give us some extra problems to work, and I was trying to think what order I did them in. Okay, we looked at those. All right, before we go on to let's see. Let's look at number 6 first. All right, that's a square root. So, as I said, is wait a minute, that's a perfect square. Oh, I know what I did. I kind of I should have went over these after before we went on to these next ones. But anyway, try doing these just on your own, and then tell me what you get. Because these are going to be going back to up here. Just a few more of these each. That's what these were. These are all perfect ones. So try those, and then like I said, we'll go on to the other page. I should have went over these next. I wasn't. Forgot about what I had even done with them now, but I remember now. See, this one right here is perfect because 3 goes into 54. X to the what? When you find out, I'll write it up there.
Three times 18 is 54.
Yeah, so this is X to the 18th. This one, like I said, is you can break it into 2 if that helps.
Yeah.
So the square root of 100 is 10, right? And 2 goes into 4. Try doing all of the rest of them should be a perfect square. Because I wanted to give you another couple of the division ones, and like I said, I've forgotten I'd written them over here. I was thinking these were all for the next page. Hold on a second. I'll get it back to you in a second. All right. Just go ahead and do that. So what is this one going to be? What about 7? Anybody come up with anything yet?
6, 8 to the 50, 15.
See, if you wrote, if we intended to write 6 squared rather than write 36, then we could play the same game with all of these by just taking half of each one of those variables. I'm sorry, the exponents. So that means 6 squared half is just 6. 8 to the 10th, half of the 10th is 8 to the 5th. And then here, 2 into 15, 30 goes 15 times. And that's a 2 there. All right, this is very similar to the one we looked at, but pay attention to the rest of it. All right, what about this one? The cube root of negative 64 is negative 4. 3 into 9. 3 into 6. How does that look?
Looks about right.
It should be exact right. But anyway.
Exactly right.
All right. Y'all try to do these. These are the ones that I wanted to give you a couple of extra ones of these to do since there was only one over there in the on the worksheet. Tell me when you get these words. 1 square root, 1 cube root. And remember, you can do this first.
I got 79x to the 4 and 2 y to, is that a 10 or a 12?
Which one?
Yeah, that's right. 4y to the 10th. So 7x to the 4th.
Okay, so number, you talking about number 9?
Yes.
7x, yeah. 7 times 7 is 49.
Uh-huh.
2 goes into 8 4 times.
And then 2y
Uh-huh.
to the 5th.
Right. And then again, if there's anything here that simplifies out, we do it. In this case, there's not. All right, so try the cubic one. They're both the perfect cubes. I'll write that middle step here.
So that would be 2y to the 5th.
I do think you're right, but just keep going.
And 3x to the 4th.
All right, so cube root of 8 is 2. 3 into 15 goes 5. Cube root of 27 is 3. And 3 into 12 is 4 times. 3 times 3 times 3 is 27. X to the 4th times 3, or to the 3rd power, is 3 to the 12th. 2 cubed is 8, and y to the 5th cubed is 15. All right. So, and then the next ones, where were those other ones at? Okay, we'll come back to those. We might even do some of those first. All right, I tell you what. Try number 15 and 16, and then we're going to take ourselves a little break. And these are both intended to be squares. I'll take them out for the sake of so there's no confusion. There's nothing there. We know it's a 2. But like I said, just when I was trying to explain it, I was showing you that theoretically there's a 2 under there, and you can use that for dividing into your radical. All right, anybody come up with those?
For 15, I got y 9 times y.
All right, let's see.
2 goes into 19 9 times. It gives you 18, so it leaves out 1y.
Right, so this is 2 into 18 goes 9 times, and 1 staying in there, right?
Yeah.
Because 9 times 2 is 18, plus that one right there.
For the next one, I got x to the 11th and times x.
Mm-hmm. With the square roots, there's always going to be just one left in there. With these other ones, it's possible. We'll come back to those, but it's possible to have one inside. All right. But yeah, for the square roots, you only have one in there because it's either odd or even. These other ones will be a little bit different. All right, let's go ahead and take a break. So it's going a little bit faster than I wanted to. So we should be all right on time. I'll see you in a few minutes. So we don't generally write numbers like that, but if you can learn to do that, it might, it'll make it consistent with the variables because the variables are the easy part, I think. All right, let me see if I can come up with some other ones to ask you. I got another section, but I'm not like dying to try it yet, but we'll go over a little bit of it in a few minutes. All right, let's see if I can find something for y'all to do. Let's see. Put that in there for y'all to work. Because if you get these down, then the rest of the stuff will be fairly easy. All right, so let's see, 6 point, not 6, it's 10. 10.3. Most of them are, okay, here's a good one. Where did I stop at? It was like 16 or something like that, 18. So I'm just going to put these out for you, and I'm going to wait a few minutes, and then I'll come back and look at them. So that's a negative sign in front. So try that one. I'm going to keep looking for some other ones. these are in my math lab, so this will kind of prepare you for when you get there. That's a fifth root, but it works the same way. And since you've only got variables,
Is that for number 19? Is that 8 to the 12th?
I'm gonna go back and check. I think it is. A to the 12th, B to the 9th. And this is a G, and that's a 9. They got some strange stuff in there. All right, let me try something. All right, so and then the last one is another fifth root. All right, so let me start off with this one and see. You just tell me how it looks. All right, so this is negative. So we gotta have a negative on the outside there, and it's a negative whatever comes out. So I'm not gonna put a parentheses there, just so we'll know to apply it. All right. So I'm just going to put that there to open up a spot. So this is 36 times 2. And then this is, well, that's going to be a perfect one. And then this is B8 with 1 left over.
Can I ask something real quick
Mm-hmm.
while we're on that step? Because I came up with 9 times 8, equals 72. But if the 8 is not a prime, does that mean it would have to be broken down?
Well, look, 8 times 9, right?
Uh-huh. No, well, 9 times 8 and 3 times 3 equals 9. So
Right, but look at here. Okay, so that would be 3 square roots of 8, right? Now, what's wrong with 8? 8 still has
yeah,
a 4
that's why.
times 2 in it.
Okay.
So see, then it's going to be 3 times 2, and then the square root of and the 2 stays inside. So
Okay.
it's 6 square roots of 2.
So it still ends up being the 6 and the 2. Okay.
Yeah, it's just that you have to do it twice.
Gotcha.
All right. Probably I didn't need to put that there yet. But whatever goes out in front is going to be negative. All right, so put all the all right, so this is the perfect square. It's going to go inside of that little spot. So 6 a squared b fourth, and then there's only a 2b left in there. You don't necessarily need the parentheses. It's just that it's just showing you, especially if there's not anything inside of it, but it's all right. Does that look good on that one? See any problems? All right. So that was a negative square root. So that negative has always got to be applied to whatever comes out. And it's like a -1.
How'd you get
So
8
it multiplies that and just changes the sign out front. Mm-hmm.
How did you get 8 to the second? Wouldn't it be to the 6?
It sure is, isn't it? I don't know what I was looking at.
Just here to keep you on your toes.
Yeah, thanks. That's what I wanted y'all here. All right, so square root of 100. So I'm going to put the perfect squares together.
Yeah.
And then the b fourth, and then that extra b is going to be by itself. So this one right here is the 100, 8 to the 6th, b to the 4th. That's the perfect square. And then that b staying in the side. So this is 10. And then we can take half of the variables. That's, to me, is the easiest way to do it. Half of the variables exponent. So there we got it. See any problems with that one?
That's what I got.
All right, so so 21 should be able to be handled just like the cube root. In other words, you don't have to be thinking about any numbers because that's all variables. So you just divide the 5 into each one, take it out, however many times it comes out to the front. Anything that doesn't come out stays in. It's a remainder.
Is that a 9? Like G to the ninth?
Yeah, G to the 9, T to the, this is those crazy, my math problems. I gotta use other variables. Oops, that's not it. What am I thinking? And just like with these, see, anything that stays in there, that power has to be less than that index. And in this case, of course, the index and the power aren't written because that's the base case of square root and b to the 1. But that's the idea. Here's the perfect one. So what does it come out to? T squared, G, and a fifth of G stays in there. See, again, fifth power, it's smaller, so you know it stays in there. Try that. Try that one. That one kind of threw me for a loop when I first saw it, but then I realized it was easier than I was expecting. So when y'all get to 22 and 23, let me know what's going on. That should be enough for right now, but so does this one look good?
Yeah, that one's good.
That's supposed to be a square there. T squared G. Five into 22 goes 4 times. And the 75y squared stays inside, because that's the remainder. 5 times 4 is 20, plus 2 is 22. The 75, there's nothing you can do about that. I mean, you could go through the trying to find it, but
Where'd you get Y?
oh, it's X. I'm sorry. I don't know why. How I got Y in my head. So you can kind of try. I mean, look at this. So if you take 2 times 2 times 2, that's cubed, times 2 is to the 5th power, that's 32, all right? So 2 to the 5th power is 32, but watch how quickly it blows up with 3. Let's see. See that? That's just the second number. 2 was 32, and 3 to the 5th was 243. So this right here is not going to break down any because there are no 5th powers between after 2. I mean, the 3 to the 5th power already way surpasses that. They get big real quick. All right, so let's see. I'll break this down. 8 y to the 9. Those are the perfect ones. The ones that are staying in are 4 times 8, right? So 4 and y squared. Those are staying in. 4 times 8 is 32. This right here is the only perfect cubed. And then if we had one more, we'd have 12. We'd have a perfect cube, but we have to take what we can get. So this right here is 2y cubed and cube root of 4y squared. All right. All right, so just for a few more minutes, let me just show you what 10.2 is about. So that way, come Wednesday, maybe we'll have this kind of out of the way. 10.2 can be a bit confusing, but let me kind of point you back over to this these exponent rules from chapter 5. All right. All right, these things still apply. The product rule, the quotient rule, the power rule. We've been using those actually. But the one that we're going to be thinking about is this last one. It's fractional exponent. And I'm probably going to have to write it over here because of it just doesn't blow up that well over there. Doesn't enlarge well. So if it weren't enough to just have exponents, now we got to have, well, if it wasn't enough to have exponents and then also fractions, now we're going to put the two together. So a to the x over y So whatever the denominator is of this exponent that's a fraction goes in the crook. The a is the base, and the x is the power. It can also be written like this, whichever one is more useful, but they both mean the same thing. So the numerator comes out, and it's a regular exponent like the numerator, like any other one. But for the denominator, that simply translates to a radical. And the radical index is whatever the denominator is here. So that's what we're doing here. And don't forget about the negative exponent rule. All right. And then I'll just remind you about that because I think the first problem has got. So what was the variable today? It was A. Okay. So the negative exponent just means we take the reciprocal. So just remember that. It doesn't mean everything's negative. It just means take the reciprocal. All right, so let's just look at this for a couple of minutes, and then we'll head out, and then we'll come back and work on the problem sets. We also have to work on 10.4, and 10.4 is a little bit long, so I want to make sure we're set up for it. All right, so if we have base of 81 and we take it to the 1/2 power, well, that's simply a way of saying the square root, because there's a 2 down there, the square root of 81, which simplifies to be 9. And for most people, like in the Western world at least, seeing one of these makes more sense than that does. So that's why we're translating it to a radical and then simplifying that radical. And the square root of 81 is 9. All right, on this one, it's 16. That's our base to the negative 5/4. Remember, the negative, as I said over here, all that means is take the reciprocal. So instead of 16, we got 1/16 to the 5/4 power. The 4th in the denominator means 4th root of that base. And then the 5 comes out to take it to the power 5th once we simplify the 4th root of 16. Thankfully, in this case, these problems are made up to be nice and come out nice and even. So the 4th root of 16 is 2. And then we take it to the 5th power. 2 times 2 times 2 times 2 times 2 times 2 is 32. And so that's simplifying. So that's probably enough for one night. If you got any questions, stick around, let me know. We're in basically now 2 more weeks. Plus that day, I guess after, before today it was actually 3 weeks. So now it's 2.5 because we got that half a week after test 5.
So Professor Cruz, we have about what, 3 days? We take
Well,
the
3 more. We got Wednesday,
we take
and then next week we got a Monday and a Wednesday,
uh-huh.
and then the following week we got a Monday and a Wednesday, which is where our test is at, and then after in May we got 1 day after test 5 and before the final. So it's, if you don't count the day, we've got 2.5 weeks left.
Right. Okay.
Before today it was exactly 3 weeks, but today now it's 2.5. So that's it.
Well, thank you as always, Professor Cruz.
Okay, you're welcome. We'll see you next time.
All right, have a good night.
Yeah,
Good night.
good night, everyone.
All right, Miss Cruz, thanks.
Okay, bye-bye.